Hello, everyone, and welcome to Lunch with a Scientist. I'm Leah from Headwaters Science Institute, and this is another chance for you to meet a brilliant woman in STEM today. So today we're going to meet Jenessa Peterson. She is a former teacher turned data scientist and engineer. Her most recent work in data science has included building a web-based voter data tracking platform, anomaly detection models for skin lesions and eye disease, and a satellite imagery pipeline for NASA data, among other things. She also supported curriculum development at Illustrative Mathematics, and prior to her work in technology, she taught English language arts for pre-kindergarten through high school students. She served as co-lead of the Sacramento chapter of Women in Data and earned a bachelor's degree in philosophy from the University of California at Berkeley. She has also edited a book on artificial intelligence in education, and she has a passion for leveraging the scientific method and machine learning technology to improve education. So she is here to educate you today on the field of data science and specifically some of her work with disease. So I'm very excited to welcome Jenessa Peterson. Hi.
Hi. Thank you for having me.
Yeah, so happy to have you here today. And you're not too far away from us either, up here in the Tahoe area.
Yeah.
We've got a lot of scientists that we talk to across the country, but you are here in California as well. So we're excited to get into your presentation, so I will let you take it away.
Okay, great. Thank you. So today I'd like to talk about what is a neural network. My name is Jenessa Peterson, and like Leah said, I'm a data scientist and a learning engineer, which means that I use the scientific method to study what works in education. Prior to this, I was an English language arts teacher for 10 years before switching careers. So I want to talk to you today about a project I did a few years ago with some friends. This project was a volunteer project that we did to help doctors in some far rural areas in India, actually, to identify eye disease more easily. So the eye disease we looked at is called diabetic retinopathy. It's a condition that can cause vision loss and blindness in people who have diabetes. And it affects the blood vessels in the retina, which is that light-sensitive layer of tissue in the back of your eye. So in a normal retina, it might look pretty kind of clean. The vessels are pretty strong, and there's not a lot of extra, what you would call maybe dots on the pictures of the retina. But in somebody who has diabetic retinopathy, they might have these little fatty areas that build up, or they might have ruptures or hemorrhages in their blood vessels. And there are other little signs that can show that diabetic retinopathy is starting to happen in the eye. And there are treatments that can help prevent the blindness, but these need to be caught early. So what's commonly done is that a technician will take a picture of using a tiny little camera that goes right up next to your eye and takes a picture of the back of your eye. So it takes a picture of your retina. This is called fundus photography. And in a healthy eye, it might look something like this, but one with diabetic retinopathy, it might look something like this. So the problem is, in these far rural areas where there's not very many eye doctors available, it takes time for a doctor to check each image carefully. So this makes this health service more difficult to provide. So the solution is to use a computer to flag only the most concerning images for the doctor to view. The idea is that we wanted to use the computer to try to make this easier on the doctor. So can a computer make a decision without you having to program it? This is essentially the question of machine learning. Maybe you've used a computer programming language. Maybe you've written some code in Python or JavaScript. When you have to plan out each step that the computer will take, that's programming. But when you instead plan out the steps that the computer will take in order to plan out its own next steps, essentially the computer programs itself or teaches itself what programming will make a good choice. That is called machine learning. So looking at a lot of these images can be really time-consuming and tedious for the doctor. And this can lead to mistakes too, because they just look at so many images and their eyes kind of start to cross by the end. But we can teach a computer using in this case, using a model called a neural network, which I'll talk a lot about today, to identify the images that show signs of this disease. Then the job isn't done. The doctor still needs to look at those images, but maybe instead of looking at, say, 3,000 images, they might look at 8 images. And their job is a lot easier at that point if we can use this machine learning to make it easier for them. So maybe you've heard that computer models can do this. You might have heard of computer models that can tell whether an image has a picture of a cat. You might have seen or heard something about that. A computer could do this. It could look at this image and say, does that have a cat? Does that have a cat? Does that have a cat? And they'd probably get pretty good results. Or maybe you're a fan of the TV show called Silicon Valley. I know I am. I really love that show. In that show, they made a hot dog or not hot dog model, and it made them rich. But maybe you've heard of facial recognition. Maybe you've noticed that your phone, some people have kind of advanced phones where you don't even have to use your fingerprint. You just look at it and it recognizes if it's you. And it can identify you in all your pictures and can also identify your friends and family as separate individuals. That's image recognition, just applied to the realm of faces. And actually, the fingerprint recognition is image recognition as well, because it's identifying the swirls on your finger as different from other swirls. You might have seen or heard of computer algorithms being able to detect multiple things in the same image. And it can track the location of those things. This is used for self-driving cars. There's a lot of applications for this. And it all begins with being able to identify what is in the image. So it really starts with object recognition. So how do they do this? So we use a neural, there are lots of ways for a computer to learn. As we talked about, when we say learn, that just means that a computer, instead of being hard-coded or programmed to do a series of steps, it is programmed to adjust its own programming in response to seeing a lot of examples of something. So there are lots of ways for computers to learn. And one of these ways is called a neural network. When you use a very large neural network, you call this a deep neural network or deep learning. A commonly used type of deep neural network that's used commonly for image recognition is called a convolutional neural network. Now today I won't talk very much about what's the difference between a convolutional neural network and other types of neural networks. But you can at least know that there are multiple types of neural networks. Neural networks are actually modeled after the brain's neurons. So if you think about, if somebody asks you, what's 2 plus 2? There are parts of your brain, neurons in some areas of your brain, that have to figure out just figuring out what the word what means. And another area of your brain, there are neurons that have access to your math knowledge and your ideas about digits. And there's another part of your brain where there are neurons that have connections that codify your knowledge of what plus means. All of the information in your brain is stored in this huge, vast connection of interconnected neurons in the brain. And it's really, really hard to determine, even for scientists, to determine what each individual neuron does. But we know that by their vast connections, they codify all your knowledge of the world, and all of your ability to participate in the world is a function of these neurons connecting with each other. So this is a more kind of cartoony version of the drawing we just saw. If you imagine neurons sort of like a web that has little fingers that reach out and grab information. And they will grab information from other neurons. And they get these messages from one end into one end of the cell. And these messages, if there are enough of these messages in collected, then the cell will fire and the message will continue to its other end, where it will release more chemicals for another neuron to pick up. There's this really important thing about neurons, which is that they have this fire or not fire capacity. So they collect messages from other neurons, and only if there's enough of those messages will the neuron fire its own message to tell other neurons about what's happening there. So this message, let's say they had enough messengers spreading the message, and so this neuron fired, and then it sends its neurotransmitters to the next neuron that collects these messages, and then maybe that has enough, then it fires, and it sends more messages to the next, and then that fires, and on and on. That's essentially how the neurons in your brain communicate. So it collects these messages on one end, and then it fires its messages out the other end. And the really important thing is that it has to collect it has to have at least enough messages to fire before it will fire at all. So neural networks are similar to the brain in some really important ways. And this is where they were inspired by the structure of the brain. So these factors are really important about neural networks. One thing is that neural networks, computer neural networks that is, are made up of many connected nodes, just like neurons in the brain. And it has many points to make a decision to fire or not fire. So similar to this scene, every time one neuron connects to another neuron, which connects to another neuron, which connects to another neuron. There's a decision that has to be made at this point based on the incoming information from the neurons before it. This is similar in a computer neural network. So this is a very simplified version of a neural network. And the simple idea is that you'll have a series of input, you'll have a series of input information. And these inputs are all connected in a similar way, like neurons, to other places of input for information. And those are connected to other places of input for information, and on and on and on, just like in the brain. So you can have a really complex neural network with lots and lots, say thousands of these nodes, which would be analogous to synapses or analogous to neurons in the brain. And thousands of these connections between these nodes as well. So what does this have to do with the eyeball pictures? Well, if you're looking at a picture and you're a computer, the way that a computer sees is to record information about the value of each tiny little dot on an image. We call these tiny little dots pixels. You probably have heard this before. But a pixel value, you could say that it's a higher number if the pixel value is lighter, and it's a lower number if the pixel value is darker. So you can see here that this sort of blurry picture of Abraham Lincoln was turned into a series of numbers, and this is really how the computer would see this. And let's say we're going to look at each of those pixel values one by one. So if we were just looking at the first 3 pixels in this image, we would be looking at this. But let's try this out on a super simplified version of our eyeball picture. Let's say we're looking at this and we're trying to determine if it has diabetic retinopathy. So in reality, this image would probably have a lot more pixels. But let's just say we're going to look at this first set of pixels right here. And these are the values for each of these pixel boxes. 3, 1, and 2. So let's start our neural network with that input information. Let's take the input values for those pixels in turn and put them in our input layer. Then let's give a covariant. This is a number we're going to use to multiply the number in the input value. This number, to begin with, we'll just start with any number. It actually can start, we do start it with random numbers, and we will adjust this later to when the computer, quote, learns. The computer will adjust its own numbers for this later. But for now, let's just take a guess. Let's say that this input value should be multiplied by 2 here and here, and actually I did the same for all of them here. And so if you take this 3 and multiply it by 2, the result will end up on the next layer. And so each of these are the same numbers, so we have a 6 on each of these. Now let's do the same for the next layer, the next input pixel. So this pixel has a value of 1, if you remember, if you remember that had a pixel value of 1. And in this time, I'm going to give some of the connections of a weight value of 1, and some of them I'll give a little more value of 2. So I'm going to add a 1 here and here and here, but on these last 2, I'm going to add a 2. Because 1 times 1 is 1. 1 times 1 is 1. 1 times 1 is 1. 1 times 2 is 2. Okay, so we'll do the same thing. Now we have those numbers adjusted from the previous layer. We have 7, 7, 7, and then 8 and 8. Now we're going to give some new random weights to the connections from this third pixel. And we'll multiply those and give it the new value numbers and add them to what's already in the next layer. So this is what we have: 13, 9, 9, 10, and 12. After we've added the input layer multiplied by the weights from that connection onto each of the nodes in this next layer of the neural network. So here's the point where it's a lot like the brain. We have to figure out, should we fire or not fire? Similar to the way a neuron takes in information and will only fire if there's enough information to pass that message along. The same thing happens in a neural network and a computer model. We have to apply a function to push this to either fire or not fire. There are multiple functions that are used for this. Just to name some, you might have heard of a sigmoid function or a ReLU function or a tanh function. There are several different versions of functions that can do this, but basically the point is to push this number to either a yes fire or a no don't fire, just like in the brain. So for our example, let's use the function that if it's larger than 10, we'll say yes, and if it's 10 or smaller, we'll say no. So where we had this 13, we're going to say yes. 9, we'll say no, no. 10 we'll say no, and then 12, yes, that's greater than 10. Okay, great. So we have our answers. Let's change those yeses and nos into numbers now. So now if there was a yes there, we'll put a 1, and if there was a no there, we'll put a 0. So this is what our new layer looks like. And now, going forward, we can apply new weights to the connections from this layer and apply that to the next layer, and on and on. So when we do this, to teach the neural network, the word we use is train. When we train the neural network, we already know what the answer it should be in the final layer. And so we take what answers we get and we compare them to what we should have gotten. And that gives us a number. We use that number to do what's called backpropagation. So backpropagation uses some calculus, and I won't go into too much detail about how it's done. But the main idea is that we use the difference in the desired value versus what we actually got to adjust the weights that we apply to these connections between layers. And we'll do this all the way throughout the whole neural network for all the weights. If the final answer was pretty close to the answer that we should have gotten, then the adjustments here will be smaller adjustments. But if it was pretty far off, there might be bigger adjustments to these weights. So when we're teaching a computer algorithm, we're teaching this neural network what weights should be on those spots. We show it hundreds or even thousands of images, and some of them have eye disease and some of them don't. So we had to find a lot of images to train our network to recognize which ones were actually showing eye disease. And we had to find images for which we had answers already. We had to know, does this contain diabetic retinopathy or not? Because that was the answer, essentially the number at the end that we could use to compare and adjust the numbers in the back propagation process. So we train the neural network again and again, comparing the answers we expected to the answers we got each time on these hundreds or maybe thousands of images. And each time we adjust the weights on that layer going back. Once we have adjusted the weights on the connections between these layers so much that we seem to be getting it right most of the time, then we say we have a trained neural network. Now we can feed a new image where we don't know the answer. And because the weights in our neural network have been so finely tuned by looking at so many examples and readjusting the weights between these layers, our neural network can now determine if there's diabetic retinopathy in an eye picture for thousands of pictures. We can pass the pictures through, and hopefully the idea is that it will really help the doctor narrow down which pictures need a second look. So the same doctor can help a lot more people, and you can reduce the cost of this service for people and help people in places where there aren't enough doctors to help that many people at a time. So it really makes a big difference in people's lives, all because we use a computer algorithm to take on some of the work for us. So that was one project with machine learning and a neural network. Questions?
Thank you very much, Jenessa. Oh, there you are. That was fascinating. Really interesting to hear how machine learning can impact our daily lives. And I wondered if you might be able to give a couple more examples of the way that machine learning is used in other healthcare applications. Do they have to be photos, or could it be like a heart scan looking at clogged arteries or things like that?
Yeah, that's a great question. So for photos, you can look at any kind of photos and finding, in mammograms or in X-rays or anything, you could find small things that are kind of difficult to see because the image recognition will do that. But you can also use, say, like an EKG, which is time series data, and you can look for patterns in that as well. That's another type of machine learning. But yeah, yes, you can use that to look for patterns in the way your heart beats, or you can use machine learning to look at data collected, say, about a patient's age and their diet and their ethnicity and their all the things and their time of arrival at the hospital, etc. And they can identify patients who might be in the most risk of an adverse situation where they might need extra help. So there's a lot of things you can do in medicine with machine learning.
Interesting.
Yeah.
That's fascinating. And so you told us about just this one project that was really specifically used for the medical field, but I know from our talks off the screen here that you as a data scientist have done many, many things. Can you tell us a little bit more about some of the diversity you've had in your career? Yeah,
so a lot of my work so far has been in image recognition, but image recognition can be used in a lot of different things. One thing is we created a tool that could be used to sort through really large amounts of satellite data from NASA's satellites of the Earth, satellite images of the Earth, and could identify storms that are happening possibly earlier than they might recognize them, or cloud patterns, or different issues that might be available in these, such as hurricanes or things like that. In that case, there's so many images that it was really a project of making making it easier for scientists to make just a few labels, and then allowing those labels to train a neural network with fewer labels.
Interesting. And I wonder about those neural networks. You talked about those and then how we can get to a deep network. It seems like there's so much more technology with machine learning now. So are humans getting better at programming the computers, or are the deep neural networks getting more complex where the computers are actually teaching themselves?
That's a great question. I think it's a combination of both, definitely. It's also a really big factor is how many example pieces do we have? Because if you are going to train a neural network, the more data that you have that's already labeled, the better your algorithm will end up being in the end. So the more we start to realize the value of having images labeled, or having EKGs labeled, or all the data that we have, that's really pushing a lot of the innovation in this field, is just having a lot more data to use to train.
So we do still need those human labeled samples and seed data to help with the training process.
Yeah. And we just build on that exponentially, I think.
Right.
After year.
And so we all heard in your bio that you had a different past than data science. You started as an English teacher. And I think that for some people, maybe not finding your career path right off the bat might be a little bit frustrating. But for you, it led you to something really fascinating and interesting. And can you tell us about that journey and how you found data science?
Yeah. So when I was teaching, I just took a programming class for the fun of it in Python, and discovered that I loved it. I really love logic and symbolic logic, and programming is really a lot of that. And so I took a few more classes, and before I knew it, I was starting to gather a lot more skills in the area. And I started thinking about how data science really feels like this powerful tool. You know, it's like Thor's hammer. You can just, you can do so much with it. And in education, I wanted to make an impact that was possibly bigger than just my classroom. And so I'm really working even now to find the places where I can wield this hammer of data science to help improve the way we do education. Because we can study how we teach with the same sort of rigor that we use to study ocean plant life, or the way we use to study the stars. Today, with the data you can collect, even just from a video camera, you know, from webcam data, or from the speech recognition, from the teachers speaking, their voice inflection. There's so many ways to collect so much data that could help us to really study what qualities make a teacher a good teacher, and can we replicate that for more students, so that more students get teachers who use these traits we find scientifically to be good teaching traits.
Interesting. So we can analyze the way people work as well with data science.
Yeah.
That's fascinating. And
yeah.
it sounds like you wouldn't have found this if you hadn't gone in a different direction to start with and become a teacher first. So I wonder if you have any advice for the students that will be watching this who don't quite know what they want to be when they grow up and maybe like science but aren't really sure and want to just try a few things.
Yeah, I think that's a great question. I really think you may have heard this before, and you probably I wonder what you think about this, but I think you should follow the next shiny thing. You know, so what sparks your interest right now, you never know how that's going to lead into something else. So follow your passion for now, put everything you've got into it. And if you start to see that now you want to move somewhere else, you can adjust your driving down the line. But you don't have to worry so much about making your whole life plan when you're just starting out.
Mm-hmm. I would certainly agree. I've been many jobs as well in my life. Um, but how about for the kids who maybe really have accidentally or intentionally been exposed to computer programming or some kind of data science already and know that that's what they want to do? What would you recommend for them as their educational next step?
Okay, well, one, take all the math you can get your hands on. That's really key. And take computer programming classes. I would recommend taking multiple programming classes in multiple different languages, but you don't need to specialize in every language that there is out there. I would say maybe 2 or 3. And then try making some stuff. That's the really key thing. If you like computer programming, try making an app and just see what happens. You might run into, you're going to have to Google a lot of things that you don't already know. And you're going to have to ask for help, find teachers or other people who are doing interesting work, and ask them if they know what you should do to solve your problem in your app. And find a community of people who like to talk about this stuff too. I think that's really key, because all of this is so much more fun when you can share it with your friends, people who also like, you get the light in their eyes when they start thinking about programming or data science. There are quite a few places you can do that. And so one of them is through school. You can sign up for data science as a major in college. And there's lots of programs for that now these days. Now there are, and related around the periphery of that as well, and computer science and math and statistics as well, or data analysis. But there are also other ways to find your community around that. There are a lot of online resources as well where you can sort of teach yourself at home. You might use Coursera or edX or DataCamp. Those are some of the better. DataQuest. There's a lot of great online resources to start learning this right away.
Great. Thank you so much for sharing your wisdom. And I do want to wrap up talking about resources. Jenessa is part of an organization that brings together different educational organizations who are working in data science. Will you share a little bit about that for the teachers and students who may want to use these resources?
Sure. Well, actually, there's 2 organizations I'd like to talk about. I work at the Learning Agency, where we bring together organizations that are working, a lot of them in data science, but some of them in just plain research, all focused around studying what works in education. And so we have a community online. We host events, and we have a lot of resources, calendar of events, and all kinds of things that you can find on our website, thelearningagency.com. And then another organization that I've been involved with a lot that brought me a lot of resources was the Women in Data organization. And that is a good place to find community with other people who are involved in data science and data analysis. And they host events. There's, I think it's womenindata.org, I'm not sure, but that's the organization. And there are lots of other organizations with focus on data science where you can find your tribe.
Great. Well, thank you so much for the resources. We will post them along with this talk later on. And we appreciate you sharing your wisdom today. Thanks very much.
Thank you.